Good afternoon, everybody. Let's get started with the class. For announcements, the solutions to the homeworks and quizzes get posted right after you submit them, basically a few minutes later. So you can see the solutions for quiz one, and I think that the homework was due, so you can see that one out there too. So take a look at those solutions. Let me know if you have any questions on those. You have some upcoming assignments. Check out those due dates on Canvas and due times. Those are posted. The pre-lab, next quiz, and next homework are all out there. Don't forget that lab one is due on Friday. I think it's 9 a.m. There's one report due per team. So generally the lab reports will be due 1 week after you perform the lab. And then pre-lab two is due Thursday. That's generally due the night before you perform the lab. So that's coming up. The TA office hours are mostly posted. I think we have 2 sets of office hours out there. We'll get the third set posted shortly. And if you have any questions during class, be sure to shout them out or shoot me those questions in the chat or stop by office hours right after class. And let's talk then. All right, so let's continue talking about sources. We started sources last time, and I want to bring this slide back up, talking about the types of sources that we're mentioning here, that we're studying here. We're studying voltage sources and current sources, and both types of those sources have independent and dependent versions. So there's this quad chart of sources we're covering here. We talked about ideal independent voltage sources, and these create a voltage between 2 terminals or maintain a specified voltage between 2 terminals. And I gave a couple examples to a very rough order. A battery can be modeled by an ideal independent voltage source, sort of. We'll talk about that later when we get the Thevenin equivalence. Function generator can represent an AC source. And then we talked about ideal independent current sources. And so current sources maintain a specified current through the source. The example that I presented was, well, a constant current battery charger is a really good example of a constant current source or an ideal independent current source. And although I have these sources drawn here, not connected to anything, they have to be connected to something so that the current can flow. So there needs to be a circuit connected to these terminals. So those were the independent sources, voltage and current, that we talked about during the last lecture. I want to move on to the dependent, also called controlled sources. So an ideal dependent voltage source is a voltage source that is controlled by some other current or some other voltage in the circuit. So here's the schematic symbol of a voltage-controlled voltage source. Remember that a diamond means dependent. If you see diamond, that means dependent or controlled. If you see polarity markings within the source, that's a voltage source. So this is a voltage-controlled voltage source. So this voltage source has a specified voltage right here. It's dependent on, it's 9 times Vx. That voltage, Vs, is dependent upon some other voltage in the circuit, Vx. We say that voltage Vs is controlled by voltage Vx. So if Vx changes, that means Vs changes. Okay, and then you would have that voltage applied to the terminals here, the output. Okay, so there's a fairly straightforward example of a voltage-controlled voltage source. One good example you probably have experience with, an audio amplifier is a good example. So an audio amplifier creates a voltage at its output terminals where you connect the speakers. There's a voltage. And that voltage at the output to the speakers is controlled by an input, the audio input to the amplifier. So that's an example of a voltage-controlled voltage source. We'll see later when we get to Thevenin equivalent circuits, you actually need a resistor in there to model the audio amplifier output. But this is a good example to start with, to say Here's an example of a voltage source that's controlled by some other voltage. Then there are uh, current-controlled voltage sources. So this is also a voltage source, but the controlling factor is another current or is a current. So this voltage Vs is controlled by current Iy. So Iy is some current somewhere else in the circuit, and somehow in this circuit, this controlled voltage source knows what that current is, and it's creating, in this case, 11 times that current. And that voltage is then applied to the output terminals. So voltage Vs is controlled by current Iy. Okay, it's dependent on current Iy. A good example of a current-controlled voltage source is the circuit you would use for a photodiode light sensor. So a photodiode or a photodiode light sensor produces a current. You can set it up so it produces a current that is proportional to light intensity. And so maybe you want an output voltage that is a function of the light intensity. And so you can use something that's a circuit that is modeled by a current-controlled voltage source to create a voltage based on the current flowing through the photodiode. All right. So those are controlled voltage sources. One's controlled by voltage and the other is controlled by current. Okay, but they're both voltage sources. There are also dependent or controlled current sources. So the ideal dependent current source is controlled by some other current or voltage in the circuit. Here's the schematic symbol for a current-controlled current source. So it's controlled or dependent because it's a diamond, and it's a current source because, well, it has a reference direction shown inside of its symbol. The specified current for this current-controlled current source is 3 times Ix. So this current Ix is controlling that specified current Is. So Ix is some current somewhere else in the circuit, and that's what's doing the controlling here of this current. So you'll get 3 Ix flowing out of this terminal into the bottom terminal to the rest of the circuit. A good example, which we will cover in this class, that is modeled, this component is modeled by a current-controlled current source, is a bipolar junction transistor. We're going to study these. And so this is a BJT, and here's the schematic symbol of a BJT, bipolar junction transistor. And what happens here is current IC is controlled by current IB. We're going to look at that. This is the symbol. Again, it's a controlled current source, and I have a voltage doing the controlling. So this is a voltage-controlled current source. Voltage Vy is some voltage somewhere else in the circuit, and Vy is controlling Is. So if Vy changes, then Is changes. So current Is is controlled by voltage Vy. Okay. And a good example, and someone had just mentioned this in the chat. They said, "Are we going to be working with MOSFETs as well as BJTs?" I'm going to mention a field effect transistor here. That's a MOSFET is a type of field effect transistor. We're not going to cover those. We actually cover those in the follow-on class to this practical electronics that I teach. But we're going to cover in depth the bipolar junction transistor, so you can build things like electronically controlled switches or amplifiers. And then for motor controllers, typically for higher current, you would use MOSFETs. But I'll refer you to the next class just because we don't have time to fit that into this class. But the field effect transistor is a good example of a device that allows a current to flow that causes you could build a current source with this, but that's controlled. The current is controlled by the voltage between the gate and the source terminals here. Okay, so if you model a field effect transistor in a circuit in a schematic, you can use a voltage controlled current source, okay, within reason, right? You have to have the right circuit, but this is a good example of where you would use a voltage controlled current source to model a component. So we've covered these 4 different types of sources. Just to remind you, we have current sources and voltage sources, and we have an independent voltage source and an independent current source. These are those 2 schematic symbols. When you have a circle, right, with a polarity or a reference direction, that means independent. When you have a diamond, that means dependent or controlled. Okay, and the controlled sources can be controlled by voltage or current. So that's the summary of sources. Let's work a clicker problem. So here is a circuit. Let me get the clicker software running here. So here's a circuit. These blue boxes are circuit elements. Doesn't matter what they are. You do have a couple sources here. Here's a source here. Here's a source here. I have a current labeled I sub B. I have a voltage labeled V sub X, and then specified current and voltage for those sources. So find IB. What is IB? So just to talk you through this a little bit, there's a relationship between IB and IS that you could see here. IS is dependent on Vx, and Vx is defined here across this circuit element. I'll call time on this. So we have a current source, a dependent current source, whose current is 4 times Vx. We have to figure out what is Vx. So Vx is the voltage across this circuit element. It's the voltage between these 2 nodes that I'm pointing at here, left and right of that circuit element. A couple ways you can figure out what Vx is. You could work a KVL equation, right? I can go around this loop and say -5 plus Vx equals 0. It's one way. Or you could recognize, hey, both of these circuit elements, this blue one here and this voltage source here, they're both connected to the same 2 nodes. And if 2 circuit elements are connected to the same 2 nodes, then they have the same voltage across them, assuming they have the same polarity defined. So we can figure out Vx, and then we can figure out Is, and Is is the same current as IB. Okay, so IB is equal to Is, 4 times Vx. Vx is the voltage between the red and the black nodes. Vs is also the voltage between the red and the black nodes. So Vx equals Vs, that equals 5 volts. So Is is 4 times 5, 20 amps. That's what IB is. Okay, so that's how I would solve that problem. But it does show an example of, well, what does this mean? Where is this Vx in the circuit? Well, it's someplace else in the circuit. How does this source know what Vx is? Well, we'll talk about some examples later, but for example, that's how a transistor functions. It has more than 2 terminals, but a bipolar junction transistor either has one current that is a function of another current, or a MOSFET has a current that is a function of a voltage. And we have to talk about those specific circuit elements to dig into that. But for now, we're working at this high level circuits schematic level here. So you just kind of accept that this controlled source somehow knows what Vx is, and its current is controlled by that voltage Vx. Okay. Someone asks, if the reference direction for Vs was flipped, would I be negative 20 amps? Yeah, if Vs was flipped, Vs, yes. So if I put plus on the right and minus on the left for Vs, then Vx would be negative 5 volts. Is would be negative 20 amps. So that's right. Okay, and don't worry about negative voltages, negative currents. Those values are just fine when they turn out to be negative. Okay. All right. Let's continue on talking about resistors and Ohm's law. So you've probably seen resistors and Ohm's law before. Let's point out some ways you can get yourself in trouble using Ohm's law. So let's start at the beginning. A resistor is a device that behaves according to Ohm's law. That's very generic, right? This is the schematic symbol here. And you say, well, I've seen resistors in lab. They look like those, they have the stripes on them indicating, the rings on them indicating the color code. That's the value of the resistor. Um, but actually, other circuit elements and devices can behave according to Ohm's law. For example, a speaker within a certain range of frequencies, of audio frequencies, largely behaves like a resistor, or the input to a radio receiver, when it's designed well, largely looks like a resistor. It obeys Ohm's law. So resistors are not just circuit elements that you put in your circuits and you work circuits problems and you dissipate heat, but resistors and Ohm's law also apply to these devices that just behave according to Ohm's law. So this is how we're going to define voltage and current and resistance for Ohm's law. I've drawn the voltage V here with the polarity, the positive polarity or the plus on the left, negative reference polarity on the right. And I have drawn the current into the positive side of the reference polarity. And then I'm defining R to be resistance. And so if I've defined it this way, voltage, current, resistance, then Ohm's law is V equals IR. Okay, so voltage is equal to current times resistance. Resistance is in units of ohms. If you divide both sides by I, you'll see an ohm is actually a volt per amp. Okay, but we've decided to call that unit ohms. Resistors look like this. So here are leaded resistors that have, looks like various values here. So these are the types of resistors you have in your lab kit. These are surface mount resistors, so you can see the metallized edges on this. Those are the two terminals of the resistors. Those get really small. They're generally used on surface mount circuit boards where you don't have holes through the board. You solder those right to the surface of the board, either by hand or different soldering techniques, like a reflow oven. You can see the size of these resistors on the strip that they're often put on reels for pick and place machines. So there's a quarter and there's, you can see they're actually fairly big resistors nowadays, but you get an idea of the relative size. One thing to note where I said you might get yourself in trouble is note the reference polarity and reference direction whenever you're working Ohm's law. For example, if I have a 10 ohm resistor and I've defined voltage like this is voltage V1 with plus on the left, minus on the right, and I have current that I've measured, I1, going from left to right through this resistor. So this configuration of reference polarity and reference direction matches what I have drawn in the upper right for Ohm's law. I have the current drawn into the positive side of the reference direction for V. That matches this down here. So this is a straight application of Ohm's law. V1 equals I1 times R1, 20 volts. But let's suppose you're working in a circuit. Maybe this is a resistor in a bigger circuit. So you have certain voltages and currents already defined, and you find yourself in this situation where you have V2 with the negative side of the reference polarity on the left, positive side on the right, and I have current I2 going from left to right through this resistor. And let's say I know the resistance is 10 ohms. Well, I have the reference direction arrow pointed into the negative side of V2. But that's not the case up here on the right. For V equals IR, you need the arrow, the reference direction, pointed into the positive side. So what you can choose to do is you could either flip V2's polarity, its reference polarity, and call it minus V2, right? You can do that. You can flip polarities and throw a minus sign in front of whatever was defined for that voltage. Or I can flip the reference direction of I2 and call it minus I2, right? If I flip this reference direction or I draw it from right to left into this resistor, then I have minus I2 equals minus 2 amps, and then you use that value. So I chose, in this case, to flip the current and call that current minus I2, which is minus 2 amps. And so V2 equals minus I2 times R2. Not I2 times R2, you have to have that negative sign in there. That makes Ohm's law work here. All right, so that's how you use Ohm's law. Just be careful with your polarities and reference directions. For power and resistors, there's sort of a shortcut way you can think of for calculating power. So here's a resistor with a voltage and current defined, resistance defined. Power is always I times V. So this will always work for a resistor. But what you can do is you can apply Ohm's law and do this. I could say V equals IR. So I'm going to plug instead of using V here, I'm going to say this is IR. So I have I times IR, and I get I squared R. So power equals I squared R. So if you have a resistor, it has to be a resistor. It can't be a diode. It can't be a capacitor. It can't be anything like that. It has to be a resistor or any device that behaves according to Ohm's law. You can use this. Power equals I squared R. Or I can say that I equals V over R and then swap out this I for V over R, and I get V over R times V, or powers V squared over R. So if I know the resistance and I know the voltage, I can calculate the power without that intermediate step of calculating current. Okay? And again, that only works for resistances. So oftentimes you're working a circuit that has multiple resistors or multiple resistances. And you might want to combine resistors for different reasons. Maybe it's just for analysis, or maybe you just have to use multiple resistors to either get a specific resistance value or to be able to handle the power that the combined resistance needs to handle. So let's talk about equivalent resistance. And this relates to network reduction that we talked about. Okay, so the equivalent resistance can be found between two terminals of a circuit that behaves like a resistor. Okay, so I'm saying there's a circuit that behaves like a resistor. It's not just a resistor, it's a whole circuit. So what does that mean? So that means you have this in this blue box, there's a there's a circuit, and if you apply a voltage and you measure the current, you would notice that voltage and current are proportional, or V equals IR, right? And that R value is this equivalent resistance. That's what I'm trying to figure out. What is this equivalent resistance? And what does that even mean? So if I have this circuit and I say, well, I can draw an equivalent circuit that has the same I versus V relationship between terminals A and B. Then I can say that circuit is equivalent. So if I have a resistor over here, Req, and it's some value, and I apply V and I measure I, and I get a certain relationship, and I do the same thing to this more complicated circuit on the left, and I get the same relationship, V equals IR, in this case, V equals I Req, then the left circuit and the right component here are equivalent. Okay, so if I can somehow figure out how to combine all these components in here in this circuit and have the same relationship as a single resistor, then I've calculated calculated the equivalent resistance. Okay. So how do you do this? You can apply a voltage and measure or calculate the current. Or you can apply a current and measure or calculate the voltage. And then you have a V value and you have an I value. Either way you do that, and you can calculate Req, V over I. Okay. Okay, so we're going to talk more about that. I want to hit the chat here. I saw a couple questions come up. Someone asks, so if you had a negative current, I think this is about the last slide. So if you had a negative current, would it still be negative after squaring it for power? So let's go back to this. So you see how, let's talk about this calculation right here, I squared R. Let's suppose you have a negative current. If you square the negative current, like -2 amps, you're going to get +4. So +4 times R. So whether current is positive or negative, power always becomes a positive value for a resistor. That's really important. Power is never negative for a resistor. It's always positive. Look at those squared relationships. Even if the voltage is negative, you square the voltage, you get a positive voltage squared. So P is always positive. What does that mean? That means when P is greater than 0, using the passive reference configuration, when P is greater than 0, that circuit element is absorbing power. When P is less than 0, that circuit element is supplying power. Since P will always be greater than 0 for a resistor, that means a resistor is always absorbing power. What's that mean? It means it's getting hot. Okay, if you get it too hot, it creates a little light. Don't do that for a very brief period. Um, so a resistor, which we call a passive device, it always absorbs power, and its power value will always be positive using the passive reference configuration. So that's a good question. So I can make that point too. Let's see. Someone asks, and the next chat question was, would relying on more resistors also be used to help prevent overloading the resistor and breaking it? And yeah, so by overloading, I would say this. You could, overloading, I would consider to be either you exceed it. So let me start here. Resistors have ratings. They have a maximum power that they can dissipate. They have a maximum voltage that they can handle. Which, by Ohm's law, you can figure out what the current is. It usually comes down to how much, for smaller resistor values, how much power can they dissipate. For very large resistor values, you might get some voltage breakdown there. But the answer is yes. If you needed to, for example, have a resistance of 100 ohms handle 2 watts, but you only have resistors that can cover 1 watt. They're rated for 1 watt. Then you could actually take 2 resistors. We'll see this in a second. Take 250 ohm resistors, put them in series, get 100 ohm resistors, 100 ohm resistor, and if you work through the voltage division, and you'll see that each resistor would dissipate half the power of the total amount. So you can divide the power up among resistances. That's one thing you can do. And if if you're actually designing a circuit, you put some engineering margin in there, some derating. But the short answer is yes. If you're going to exceed, let's say, the power rating of a resistor, you can use multiple resistors and reduce the power dissipated by each of the resistors. All right, that's a good question. So let's get back to equivalent resistance, and let's talk about equivalent resistance of series resistors. Okay, so you probably have seen this before in physics, but let's go through this because you may not have seen the derivation of it, and I think it helps from 2 perspectives. One, just seeing how the equivalent resistance of series resistors is calculated, and 2, it gives you some practice to see how you might figure this out for yourself in analyzing a circuit like this. So let's suppose that you have 3 resistors in series. You could have 4, you could have 5. Let's use 3 or 2, doesn't matter, but let's use 3 here. And I apply a voltage somehow. So some circuit is connected to the left here. It might be a voltage source, it might be some circuit, but there's a voltage caused between terminals A and B with this polarity. And that causes some current to flow, again, from the circuit on the left into this series set of resistors down through these resistors. And what you would like to know is, okay, if I were to take these 3 resistors and replace them with a single resistance and have the circuit behave the same way, right, same relationship between V and I, what would that value be? What would Req be? So I want to replace these 3 resistors with a single resistance, right? And the relationship between V and I would be maintained. Okay, and so remember how to do this, right? I touched on this on the last slide. You're going to um, you're going to calculate the equivalent resistance by the relationship between V and I. So Req equals V divided by I. So we have to find some equation with a relationship between V and I and rearrange that equation so we get V over I equals something. And that something is the equivalent resistance. So let's create an equation with V and I, rearrange it, V over I equals something. That something is the equivalent resistance. So I'm going to define three voltages here, V1 across R1, V2 across R2, V3 across R3, just because we're going to use that to form this equation. Okay, and let me start by writing a KVL equation. So I'm going to start at the bottom here. I'm going to say minus V plus V1 plus V2 plus V3 equals 0. Right, so there's my KVL equation. So I have voltages here. I need to figure out some way to get current into this equation so we can get V over I equals something. Let me rearrange this equation. So V equals V1 plus V2 plus V3. Right, this is the V that we care about in the V over I term. So to get that I term in this equation, I'm going to use Ohm's law. Right, so if I look at this current I goes down through R1, and I can write a relationship between I, V1, and R1. Right, by Ohm's law, V1 equals I times R1. I comes down, V1 is I times R1. Same thing for V2. I can create an equation. That same current's coming down through R2. So V2 is I times R2. Same thing for V3. V3 is I times R3. So now I have some way to get I into this equation. So I get V over I equals something. So I combine these two equations and I get V equals IR1, that's V1, IR2, that's V2, IR3, that's V3. Let's factor out an I. Let's divide by I. And so there's my answer. V over I equals something. And that something is the sum of the resistances. So Req is the sum of the resistances. And so that's where you get that equation. Resistors in series have an equivalent resistance that is the sum of their individual resistances. Okay, so Req is R1 plus R2 plus R3. If you had 4 resistors in series, it'd be R1 plus R2 plus R3 plus R4. If you have 2, it's just R1 plus R2. You can see the pattern there. Okay, so let's see. Someone asks in the chat, do resistors always dissipate power in the form of heat, or are there resistors that can dissipate power in some other medium? So I'm going to give like the answer that you could always find exceptions to. Someone can argue like, well, wait a minute, what about this case? I'm going to say yes. Resistors pretty much the power goes to heat. Why do I say that? Because again, maybe you can have resistor light up for a little bit if you apply a big voltage, big current to it, and it's going to light up, and that's some energy coming off. Or you might be able to maybe apply an AC voltage to a resistor and get it to shake a little bit, right? Get some motion in there, maybe get some audio waves coming off it. That'd be a little bit of energy, a little bit of power coming off. You could argue that, but I'm going to stick with yes. Resistors always dissipate power in the form of heat. Okay, and so if anybody has any thoughts on that, I'd love to talk about that, but I'm going to say yes. I hate to say always; it's always that case, but I'm gonna commit to that now. Okay, so this was how you calculate the equivalent resistance of series resistors. Let's talk about parallel resistors. You've probably seen this before too, but again, let's go through this exercise because I think it helps understand why this is the case. So here is a circuit. I have 3 parallel resistors. I've defined a voltage between these 2 terminals. And again, remember there's some circuit to the left here, some source or circuit that is applying a voltage. That's where the current is coming from. That current is going down through these resistors. But we're really interested in the V versus I relationship because if I have a V versus I relationship that is linear, which it's going to be for these resistors, I can calculate an REQ, an equivalent resistance value. And I could replace these three resistors from the perspective of voltage versus current. I could replace these three parallel resistors with this REQ value, and you wouldn't know the difference. Okay. I'm leaving power ratings aside here. So this is just from a V versus I perspective. Okay, let's take that same approach. Let's find REQ by creating some equation with V and I. Let's rearrange that equation into the form V over I equals something, and that something is REQ. So the first thing I'm going to do is I'm going to recognize that I have current coming in. That current splits and goes down through each one of these resistors. Okay. And so what I could do is I could create a KCL equation up top at this top node, and I could sum the currents leaving that node, and I'd get this KCL equation. Okay, so I can say I equals I1 plus I2 plus I3. Now I need to figure out some way to get a V into that equation. So let's use Ohm's law to get a V into that equation. So by Ohm's law, V is equal to I1 times R1. So V is the voltage between this top node and this bottom node. So that same V is applied across all three resistors. So for resistor R1, V is I1 R1. For resistor R2, V, the same voltage, is I2 R2. For resistor R3, V is I3 R3. Okay, so you take these two sets of equations, you put them together, you say I1 is V over R1, I2 is V over R2, etc. And I can write this equation, right? This plug V over R in for each of these I1, I2, I3 terms. Okay, so I can rearrange this. I can factor out a V. So I get I over V, or I equals V times something, divide by V, both sides. I get I over V equals, well, that's 1 over REQ, right? So I want V over I equals. So I just have to invert that. So REQ is equal to V over I, which is equal to 1 over the sum of the reciprocals of resistances. Okay, if I write that a little more cleanly, here it is. REQ is 1 over the sum of the reciprocals of the resistances. Okay, that's it. That's how you can calculate REQ for parallel resistors, and that's how that is derived. Now you'll see formulas, you'll see, well, one particular equation, and maybe even in your textbook, and some people talk about it, that I dislike because I think it causes people to use it wrong, use it improperly. So if you have only two resistors, you could say, well, the equivalent resistance is product over sum, R1 times R2 divided by R1 plus R2. And that works. And that works. You could see if I get rid of 1 over R3 here, because I have only two resistors, let's say, then I can multiply top and bottom by R1, R2, and I get what I just described, R1, R2 over R1 plus R2. I'm not writing that here because I don't want you to use it. I don't want you to use it because the problem is people try to apply that to three resistors, and they try to do product over sum for three resistors, and that doesn't work. This equation right here does not, it cannot be rearranged into the product of three resistors over the sum of three resistors. So when I calculate equivalent resistance, I just want one relationship to remember, and this is the one I remember. So I recommend using this. Okay. All right, someone mentions, a professor in the past mentioned that resistors in parallel are like lanes in a highway. The more lanes, the faster the traffic can move, increasing the current. That's true, right? So let's say that you have R1, R2, and R3, and they're all 30 ohms, right? Well, if I combine all of those in parallel, right, then I'm going, I think if I do the calculation in my head right, I'm going to get 10 ohms. So when you combine resistances in parallel, having these more lanes, right? So you can get more traffic, the resistance actually drops. So if you take three resistors and each resistor has some value, the parallel equivalent of those resistors is always going to be smaller than the smallest resistance, right? So you could add a fat lane, a skinny lane, and a skinny lane, and let's see, that the low resistance would be the fat lane, and the overall traffic you could get through is fatter than the fattest lane. Widest lane, I don't know how to describe that, but that's what that's how I would describe that. So yeah, so I'd say that you could view resistors in parallel as as like traffic lanes. That's an analogy. I like to use the fluid flow analogy. If you have three pipes, you can get more fluid through a certain pressure than if you have one pipe. Okay. All right. So I want to mention conductance. Conductance it's similar to resistance. It's the reciprocal of resistance. We sometimes use this. Um, I don't use it as much as resistance, but you should be able to recognize it. Conductance is 1 over resistance. It's given in units of Siemens or mhos. Mho is just ohm spelled backwards. So if you have a 4 ohm resistor, it's just like having a 0.25 mho or 0.25 Siemens conductance. Okay. And sometimes it's convenient to use conductance rather than resistance. For example, what we just covered, the reciprocal of the equivalent resistance is the sum of the reciprocals of the individual resistances in a parallel set. Well, you could represent that with conductance. GEQ is the sum of G1, G2, G3. That's one case where you might use conductance if you have a lot of parallel components. So conductance is add in parallel. Okay. All right. So let's talk about voltage and current division, because this shows up over and over again. It's something good to know. Um, Voltage division applies to series resistances. So here are series resistances. And voltage division is a way to calculate how voltage splits up among resistors. So if I have current going down through these resistors, and the resistors are all of different values, the voltage is going to be different across each of those resistors. And so this is a way to calculate how voltage divides, or another way is to say that it splits up among resistors. So given V, let's say you know V, let's calculate V1. Okay, current division applies to current for parallel resistors. Current division is a way to calculate how current divides, or how current splits up among parallel resistors. So I have some I coming in to these parallel resistors, and that current's going to split up between R1, R2, R3, or divide between R1, R2, R3. And this is a way to figure out, given I, what is I1, knowing the resistor values. So let's start with voltage division. So voltage division describes how voltage splits up among series resistors. So for example, let's derive the voltage division equation. So we're going to derive it once and then just apply that pattern whenever we see series resistors. Let's derive it once. Okay, so derive the voltage division equation to find out what is V1. That's an unknown, but let's say I know VS. I know that's 10 volts or something like that. And I know R1, R2, R3. I know those values in ohms. Let's figure out V1. So by Ohm's law, if I knew the current going down through these resistors, I could say V1 equals I1 R1. Also by Ohm's law, I could say, well, if I know the voltage VS and I knew the equivalent resistance, which I can calculate now, then that current I is VS over REQ, because REQ would be the sum of R1, R2, R3. So I equals VS over the sum of the resistances. Okay, so then I can plug in this I, this VS over R1, R2, R3 here, that sum. I can plug that I into this top Ohm's law equation, and I can say V1 equals VS times R1 over R1 plus R2 plus R3. Okay, so notice the pattern here. Whenever you see series resistors, you could say, I have these series resistors. I know the voltage. Let's say you're given the voltage across the series set, VS. Then the voltage across R1 can be expressed like this: VS times, on top of this fraction in the numerator, is the resistance across which you're trying to find the voltage, R1. On the bottom, in the denominator, the sum of the resistances that form that series set. So I could apply that same pattern. I could go rederive this, or I could recognize I can apply that same pattern to figure out V2. That's the voltage across R2. So V2 equals the voltage across the series set, VS, times this ratio. On top, the resistance across which you want to find the voltage, R2. In the denominator on the bottom, the sum of the resistances. And in the same way, V3. V3 equals the voltage across the series set times this fraction on top, the resistance across which you want to find the voltage. On the bottom, the sum of the resistances. And this, so this shows up over and over again. And so it's good to know this relationship. You'll use this a lot. Current division describes how, in this case, IS would split up among these resistors. And you could derive the current division equation to find I1. For example, do this. We could say, well, I know the voltage across the series, or the parallel set, not series, parallel. And I1 would equal V over R1. And then I can say V is equal to IS times REQ. So if I had the equivalent resistance, R1, R2, R3 combined into REQ, and I have V across that one REQ resistor, then V equals IR, V equals IS times REQ. Okay, and so then I could say, well, here's REQ, right? This is REQ, 1 over the sum of the reciprocals of the parallel resistors. And then I can plug that, combine these two equations, and I get this. So this is the pattern here. I1 is equal to, so I1 is the current through R1. I1 equals the current into the parallel set times this ratio. On top, the reciprocal of the resistance through which you're trying to find the current. That goes on top. On the bottom, in the denominator, the sum of the reciprocals of those parallel resistors. Okay. You could use that pattern to figure out what is I2. I2 is equal to the current coming into that parallel set times this ratio on top, the reciprocal of the resistor, the resistance, through which you're trying to find the current, divided by, on the bottom, the sum of the reciprocals of all those parallel resistors. In the same way, I3 is like this. I3 through resistor R3 is the current into the parallel set times this ratio on top, 1 over the resistance through which you're trying to find the current. In the denominator, the sum of the reciprocals of those parallel resistances. Okay, so voltage division and current division, they show up a lot just in practical circuits, so it's worth knowing these relationships. I'm sure you're going to find ways to use voltage division and current division as we go forward in this class. Even though it's not a specific voltage or current division problem, you'll find ways to use these relationships. Okay, so I'm out of time for today. So in closing, be sure to check out the assignments and the schedule on Canvas. Those are posted on Canvas. Don't forget, Lab 1 is due this Friday morning. One lab submission, one report per team. Pre-lab is due Thursday. This, pre-lab 2 going on is one pre-lab per team as well. So pre-lab 1 was different, but pre-lab 2, since you have your teams, one per team. See the Slack workspace. I've been posting some support on there, and if you have any questions, post those questions to Slack. Thanks for joining class. If you'd like to stick around for office hours, please stay up on this call. If not, I'll see you next time. Have a great night.